Well, hello, I am Professor Stephen Neshaba, and I'm here to help you out with some of the calculations you'll be doing in Spartan for the lab this week. So I'm assuming that you've already done all the other pre-lab work, which has to do with finding the number of unpaired electrons and so forth, and I'm just going to start us off into the Spartan calculations. So what we'll do here first is I'm going to just choose a new molecule here, and I've chosen the inorganic menu, and there's chromium in an octahedral configuration from the inorganic menu, and I'm going to click over there. Now this first part doesn't matter which configuration I choose, because I'm going to go to this delete button up here and get rid of everything that might have been attached to that chromium. And then I'm going to go up to the setup calculations, and instead of picking up the equilibrium geometry, which takes a little bit more time, I'll just do an energy calculation, and we want to do that at the B3 lip level. Let's see, this is just neutral chromium, that's fine, but as you probably figured out from when you did the pre-lab, there are 6 unpaired electrons, and for which I would normally just submit this, and you should do that. But in our case, on my calculator, it takes about a minute for that to run. So I'm just going to cancel that and pick up what the result was. Now, one thing about this is when we look at the model, it's kind of handy to go for a smaller ball there. So I've just chosen the tube representation. And as usual, we're going to go to the energy ladder. As you know, there's sort of this B column and the A column. We're just going to focus on the A column, and let's see, I think I've already highlighted one of those. I've chosen a mesh view and so forth, and well, here we go. Here's an orbital, and there's another orbital. That looks like a p orbital, and I'm just going to keep on going up the ladder. There's another p orbital, another p orbital. And there's an s orbital. Okay, I think that might be a 4s orbital. And now, what do we have here? We've got, you notice we're at minus 2 electron volts. That looks like a d orbital. Let's see how many d orbitals there are on chromium. There's 1, and I'm going up to another one. That's 2, 3. Is that a d orbital? Yes, I think it is. 4. And 5. So we have our d orbitals all with the same energy, minus 2 electron volts. So our next task is going to be to build the hexaamine chromium complex. So to do that, I'm going back to my inorganic menu. I've got chromium in an octahedral configuration. I'll click there, and this time I'm going to choose a ligand. And so I'm going to choose a ligand there, and I could have chosen a bunch of different possibilities, but I'm going to choose ammonia. And now I'll just put ammonias on every one of these positions. And there we go. And it's helpful to press an energy minimization button here, which I'm going to do. And that tries to get it pretty close to the right configuration. Then we will go to Setup Calculations. And once again, I want to do just an energy calculation at the B3 lip level. There we go. The total charge now, as you know from reading the handout, it's a 3+ charge, and you probably also noticed that there are 3 unpaired electrons in this complex. This is what I would normally submit, but that will take a couple of minutes, so I'm just going to cancel that and show you what the result was that we saw. Now, once again, these balls are a little bit big, so I want to go take a model and maybe do a smaller thing there. Ball and tube, perhaps. There we go. So there's our complex, and once again, we'll pick up the energy ladder. And I'll just start off here at the bottom. You'll have to probably select the mesh view. And there we go. There's the lowest energy molecular orbital for this complex. It looks like it doesn't have any amplitude on the chromium cation. This is all amine orbitals. And now I'm going to just ladder up. There we go. There's a bunch of orbitals. and so on. Some of these are sort of looking like d orbitals, and in fact they look like bonding d orbitals to the ligands, but that's not what we're chiefly interested in here. And let's see if I can... oh, well, there we go. This is looking like a d orbital, a d antibonding orbital, or perhaps a non-bonding orbital, since there's just not very much electron density on the ligands. And how many of those are there? Well, I'm at minus 20.9 electron volts. There's another one, and minus 20.9, minus 20.8. These are all looking like d orbitals of the transition metal complex. And what you'll want to do, of course, is go up to the next one, which is, oh, look at that. Look, that looks like a d orbital too, but now it's got some significant antibonding interactions with the ligands, and the energy has gone up quite a lot. So that's the basic game plan for this lab. You'll do that, and you'll also attach water ligands in addition to what we've done here.